Hello and welcome to part 1 of our lecture on rotational kinetic energy. We're going to be covering section 9.1 from Young 14th edition, and this is going to be a precursor to lectures on the moment of inertia and Newton's second law in rotational form, which are things I will hint at in this lecture. The choice to present this material is simply motivated by the fact that this rotational material of all of the rotational material is the easiest to work with. So it's a good place to start in terms of ease of problem solving. I bring this up because you may notice that starting with energy is not the way that we approach translational mechanics, where we of course started with Newton's laws and then moved on to discussing energy. So the different order, I hope seems justified, because we're starting with the easiest thing. Okay? So what is rotational kinetic energy? Well, I'm going to ask you to apply some ideas, some intuition to this approach, and to kind of to proceed on a need to know basis, and then trust that I will elaborate on and show where all of these things come from in future lectures over the next week and a half. So I say that because of this term right here, I. Okay? Why is I in this equation? What does I represent? Okay? Well, first of all, the equation that we're looking at is rotational kinetic energy. So the K is for kinetic, and the subscript rot is for rotational. So this is rotational kinetic energy. And when you look at that equation, it should look very, very similar. So we could say compare to K tran for translational, which was 1/2 mv squared. Okay? And so in that equation, the 1/2 comes out of the calculus. It comes out of the work kinetic energy theorem when we do the integral. The m is the inertia, which we call mass. That's translational inertia. And then v is simply velocity. And again, we're squaring it because of where the formula comes from in terms of its derivation and its relation to work. Well, look at this. The rotational kinetic energy has the same form. And that means that this I right here is essentially mass. Well, more specifically, it's inertia. Okay? And here we call this type of rotational inertia, we call it the moment of inertia. So I is the moment of inertia, which is rotational mass. I'm going to put that in quotes to imply that it's a less official term. Okay? And then omega, we already know from the previous lecture, is angular velocity. So this equation has the same form as the translational equivalent, 1/2 mv squared, except this time it's 1/2 I omega squared. Okay? Now, this is where I'm asking you to hold off on your rigor that you expect in this class, because I'm not going to tell you where I comes from. I'm not going to tell you very much about I, other than this quick blanket statement to say, oh, it's like mass. Okay? End of story. But of course, it's not the end of the story. And in the very next lecture, we're going to show what it means, how we calculate it, how we work with it, what is its relation to distributions of mass, and so on. Okay? Such as the center of mass. And so we'll very soon, in the very next lecture, we'll follow up on it. But for now, let's use it, right? Let's take this similarity to 1/2 mv squared and just put it to use. And that means that we're going to use it in the context of conservation of energy, because that's what this formula and this equivalency represents. This is conservation of energy, specifically mechanical energy. Okay? We could add non-mechanical energy, and this is the only time you're going to see it in today's lecture, but it's good to point out that we could add the work of friction to the left-hand side of the equation. So could add work of friction to this side. Okay? And then we would have an equation that was conservation of energy in a broader sense to include the work done by friction. All right. But if we're sticking with mechanical systems, which we will for now, then we notice that the form of our conservation of mechanical energy is very similar to what we saw before. We always had a K1 and a K2, and then we had a U1 and a U2. The only difference is that K has now been separated into two separate terms. So collectively, K1 or K rot 1 and K trans 1 is the total of K1. Together, those two terms sum to the initial kinetic energy of the system. That, what I'm saying, in other words, is that a system can have both translational kinetic energy and rotational kinetic energy. Or it could have no rotational kinetic energy, which means we might as well just be in a previous chapter, or it could have no translational kinetic energy, something that's spinning in place. But if an object is spinning and moving, or if a system consists of spinning and moving objects, then we would have both terms be non-zero, perhaps both initially and finally. Okay? The systems that we will see include things like a block pulley system, where of course the pulley could then be the rotational energy in the system. We could have a yo-yo, where there's only one moving object, but that object both translates and spins. A rolling ball is a perfect example, nearly perfect example, of a system that has both translational and rotational kinetic energy. And again, a turntable spinning in place, or a flywheel spinning in place, would only have rotational kinetic energy. Okay? So what about this term, though? How do we handle potential energy? And what type of potential energy are we talking about? Well, the potential energy that we're talking about is only going to be gravitational potential energy. All right? So U is only going to refer to gravitational potential energy. Not because we couldn't do something with elastic potential energy. We just choose not to involve elastic potential energy, and I won't do it in my quizzes either this semester. Elastic potential energy will never get combined with a rotational system. It's just a choice we made. Okay? It's totally doable, just not on the list of things to do. So here we have gravitational potential energy. And here I'm really going to employ something that we saw before, and that's the idea of center of mass. Because this form, then, so U2 would equal mg y com 2. And it has to be the vertical position of the center of mass. Because that's the only way that we can combine gravitational potential energy with rotational kinetic energy. Because if we chose the potential energy of some arbitrary point on our object, because the whole idea is that now these systems consist of objects, not particles. Particles, it didn't matter. It didn't matter. There was no center because the particle, whether we called it a box or not, was just that. It didn't have a length or a width. But now it really does, and it really matters. So if I talked about the potential energy of one corner of a block, well, that corner is lower than its middle. Thus, it would have less potential energy. And if I chose that in relation to the rotational kinetic energy of that block as a whole, I'd get the wrong darn answer. Because that wouldn't work. The actual physics tells us that the gravitational potential energy must be of the simplification of our object to a particle, because that is where the gravitational force vector acts. And that is the only point of which we can measure potential energy if we wish to relate that potential energy using that equal sign right there to rotational kinetic energy and kinetic energy. Okay? Or translational kinetic energy. So why do I make such a big deal about that? Because the equations give you the wrong answers otherwise, and it's such an easy mistake to make. Okay? Has to be the center of mass. Now, I also don't want you to think that that means we can't talk about the potential energy of other parts of the system. If I have a ball and I use this equation to find the, say, final speed of the ball rolling down a hill, and then after I find the translational energy of the center of mass, then if I want to find the translational energy of a corner or the potential energy of a corner, well, not a ball, not that balls have corners, I should say the edge or perimeter, I absolutely could. I would just have to use V equals omega r and find my V related to the omega that describes the object as a whole. But that's a follow-up step. You can't do it in one sweep. You have to only focus on the center of mass. And then, and only then, once you have your answer, can you move on to talk about other points on your object. The key word there being object. Okay, my rant is done. But I will elaborate on this one last bit by pointing out that the translational energy here also has that same restriction. Because the only way that we can sum up rotational and translational terms is if the translational terms refer to the center of mass. So this right here would be 1/2 mv com squared. Because otherwise, again, right, just I thought said I was done, but I'm not done. If the velocity was the velocity of the edge of our spinning system or spinning wheel or whatever, well, that's going to give us a different value. It has to be the velocity of the center. Okay? Just like it has to be the potential energy of the center. And not the geometric center either. Notice it's the center of mass. Now you might be like, wait, aren't those the same? Well, not if you have an uneven distribution. Okay? More on that later. All right, so that's it. There's no key terms here. The only thing really is, rotational kinetic energy, and it shows right up in the equation, so I didn't represent it as a key term. Okay, moment of inertia, you might think, okay, well that's a key term, but it's gonna have its time to shine in the next lecture. Okay, so that's it. It's just these equations, and use that similarity. Use the idea that we already know how to work with energy, because really you already know how to solve these problems. So let's do it. Okay, so I'm going to solve a couple of short problems here, and in the second half of the lecture, we're going to elaborate on some of the longer problems. Okay, so as well as doing a conceptual question. But let's take a look at example 1. Here we have a purely rotational system. A uniform cylinder with moment of inertia I equals 1/2 mr squared. Okay, what's that? That's weird, right? Well, that's just the formula for the moment of inertia of a cylinder. More on this later. For now, just take it at face value. That's a formula. We're going to use it. We're going to use a given mass for our cylinder. We're going to use a given radius for our cylinder. It's large, about 6 feet across. And we're going to then notice that our cylinder is accelerating at a constant rate. Okay, it has an unmoving fixed axis. That's how we know it's purely rotational. And then we're asked finally, how much kinetic energy does the cylinder possess after it's completed its 7th rotation? Okay, so certainly I've chosen this as a bit of segue and reminder of the material that we saw before spring break. So the first thing we need to do is we need to say, okay, well, we're asked for kinetic energy. So we know we're going to want rotational kinetic energy of 1/2 I omega squared. And then we also know that the kinetic energy of translation is 0 because it's unmoving, okay? Because the center is unmoving, and that means nothing's translating, okay? The object as a whole is not translating. It doesn't matter the parts of it are translating, okay? Because, again, remember, omega describes the object as a whole. That's why it had to have the vector that points perpendicular to the plane of rotation, because that's the only meaningful direction for that vector, if that helps you understand the concept. It may or may not. Okay, now, let's then find omega, right? Because we're given alpha, and we're given a displacement, but we don't have omega. Well, that means we need to use a kinematic equation that's going to give us omega final given an acceleration and a displacement. And so then we find omega from omega squared equals omega naught squared plus 2 alpha times delta theta. Okay, and in this case, that's going to become, well, let's point out some things that we know. We know that omega naught is 0 because it starts from rest. And we know that delta theta is going to be 7 times 2 pi because it's 7 complete rotations. So 7 times 2 pi. All right. And so then when we go to solve for our final angular velocity, we're going to get 2 times 0.34 radians per second squared times 14 pi radians. Okay, and that gives us a value of 5.47 radians per second. All right, looks good, looks good. There we are, okay. And so now we're ready to plug into the kinetic energy formula, rotational kinetic energy. Okay, so again, I'm going to use the equation that I was given for its rotational mass, the moment of inertia, as we call it, okay, which has its own 1/2, remember, right? That doesn't count as the 1/2 for the energy because it doesn't come from the same place. And then we have our 120 kilograms, and we've got our 1.11 meters squared. All right. And then we'll be multiplying that by our final angular velocity, 5.47 radians per second. And that's how much energy our big spinning cylinder possesses, which gives us a 1,110 joules. 1110 joules to 3 sig figs. All right. There we have it. That's what I want. Okay. So that right there is our answer. No translation, just rotation. Now, let's look at a different problem here. Okay. Now, this is a problem that involves rolling. Okay. Rolling without slipping. Okay. So rolling without slipping is a key term, something you look for. Kind of like we've had this habit of looking for starts from rest, right? It's kind of code for telling us initial velocity is 0. Okay, rolling without slipping is one of those types of terms that you see in the word problem and you turn it into a simple equation, a guiding equation. Okay, and in this case we're rolling down an incline. It's 31 degrees. There's no friction or anything. Excuse me. And we're interested in the final velocities of our 3 different objects. Okay, notice this, each object has its own moment of inertia, its own rotational mass. Okay, now that's because rotational mass, shape matters. You know, if I have mass, translational inertia, and I have a block of clay and it weighs 5 kilograms, and then I have a long, you know, like trough of clay that also weighs 5 kilograms, the different shapes don't matter. They weigh the same amount. But when you're spinning something, the shape matters. Think about it, right? That's why you can have a lever, okay? Shape matters. So, also, rolling is a topic that we will cover next week. It's something we're going to get into. Now, why is it here? Well, because we can approach it from an energy point of view just fine. We absolutely have the tools to do that. But once we introduce the idea of Newton's second law in rotational form, then we can do a lot more with rolling. Okay? So for now, we can do a bit with it. Expect more later, just like expect more later on the moment of inertia. All right? So let's draw our incline. Something like this. Okay, so now I have a 31 degree slope, so it'll be coming down. Okay, that's not what I want. There we have it. Okay, and this will be our horizontal direction, like so. Okay, make that a dotted line. So this is our angle, our 31 degrees. Okay, we call it theta, but we know it's 31 degrees. Okay. And then we're going to roll our different things down it. From the side, our solid cylinder, our hoop, and our spherical shell, basically just a not solid sphere, okay, would all look the same, right? They'd all have a circular cross-section, so we can kind of draw those, right? Or one thing to represent all 3 of them, okay? And it's going to be at the top. We're told that it's going to be released. It's going to roll down the whole thing, right? So we need to know that release height. And so this is basically the release height we're interested in once it gets to the bottom. I'm going to call that H. We can do a quick calculation and find that H is just equal to L times sine theta. Let's do that. So H equals L times sine theta. All right. And so in this case, that would be 1.24 meters. But I'm going to go ahead and use the variable H moving on, but we can put the value here. And let me show you the calculation. So 2.4 meters times sine of 31 degrees. All right. And that's going to give me my 1.24 meters. Okay. Now, before I move on, I do want to say of the rolling without slipping part. All right. Kind of in our preamble here. And rolling without slipping means simply, and you'll see why I would use that word simply, that V equals omega r. Okay? But of course, that was one of the equations I gave you in the previous set of notes. It said, oh, these are the ways that we relate translational motion to rotational motion. V equals omega r. Okay, right? That's great. We can take that as a given. As long as you remember in the back of your head, it's not pressing for this week, but for next week, we can actually break that rule. We can have V and omega be separate from one another because that's rolling with slipping. That's something that is not quite perfectly rolling, right? That's like the perfect example that most of us can visualize. That's a bowling ball, right? When you throw a bowling ball down a lane, at first it's spinning, right? But it's spinning kind of slowly. It takes a while before that ball is rolling perfectly. For a while, it's slipping, okay? Not perfectly, because it is still spinning, but it's spinning slower than it would be considering how fast it's moving. Get it? Okay? But more on that later. So for now, we have a very important condition that's being met, V equals omega r. Okay, so we can take that as a given. So we can go ahead and actually just jump right into using conservation of energy. I'm just going to show the three cases for our three different objects. So we have our hoop, cylinder, and shell. Let's write them each on their own line. So hoop, cylinder, and shell. Shell is short for spherical shell. Okay. And in each case, conservation of energy will give us mgh. That's what all of them start with. So the left hand of the equation, each and every time, is mgh. Okay? And notice h does go to the center of mass. When it gets to the bottom, it's still the center of mass that we care about. Okay? All right. And that will be a full distance h, right? Because when it does get down to the bottom, you might think, oh, well, the center is still not at the bottom. Well, it wasn't at the top either. It was above the top. Okay. And so then what does it look like on the right-hand side of the equation? Well, that's where all the kinetic energy is. Okay? Because the potential energy, the release from rest at the top, is going to become pure kinetic energy at the bottom. Neither entirely translational nor entirely rotational, but it is going to be kinetic energy, because our rolling objects will be both translating and rotating when they get to the bottom. All right? And so then we got 1/2 I hoop omega squared, 1/2 I cylinder omega squared, 1/2 I shell omega squared, but that's not all. They each have a second term, the translational kinetic energy term, and that's just going to be 1/2 mv squared, 1/2 mv squared, 1/2 mv squared. Except I should be using capital M for all of them, so let me fix that. Okay, now I'm not saying they have the same v's or any of that, but that's what it looks like. Okay, now furthermore, every one of the omegas is going to become a v over r, right? And so then what each of these is going to look like is the following. All right, so I'm just going to rewrite much of it out, and I'm going to express the I in terms of the equations that were given for each of them. So we're going to have mgh equals 1/2, and for the hoop, it's just mr squared. And then our omega becomes v over r squared, and then the 1/2 mv squared is unchanged. Okay, for the cylinder, mgh, you can see why I'm writing it this way, and then 1/2, and then the cylinder has 1/2 mr squared, and then again the substitution for omega, it becoming v over r, and then we square it, and then our kinetic energy term each time. Okay, our translational kinetic energy term, same each time. Okay, and then we got our 2/3 over here for our shell. Looking good. All right. And now it's cancel time. Okay, cancel our clock. And what that's going to look like is we're just going to go through and say, oh, well, now that we've rewritten everything, we see that there's an m in every term. So m is going to cancel out. So this this result, this comparison between our three different shape objects, right, all rolling in a perfectly mechanical system, well, the mass just simply doesn't matter. Okay, I could have not even given you a value for the mass, and sure enough, I didn't. Okay, but the shape certainly does seem to be mattering, right? Because this 2/3 business and this 1/2 business, and then the fact that the hoop was just mr squared, that's not going away, right? That's going to affect the final answer. So the shape absolutely has an effect. Okay, r is also going to cancel, which is quite amazing. Okay, look at this, right? R cancels because of the substitution for omega. Oh, I have a typo though. It should be writing too fast. V over R. There we go. All right. R, okay, and that one cancels like so, okay, because it's an r squared canceling over an r squared, because don't forget, right, it's being squared. Well, why does the radius not matter? Well, because everything is going to basically have the same amount of kinetic energy at the bottom. Maybe like, well, wouldn't a really big object have less kinetic energy because it would have fewer times the spin? Well, no, because we're talking about the kinetic energy of its center. So a really big object would rotate fewer times, but it'd be so much bigger that the rate at which it's rotating would be faster. So the two effects cancel each other out. Okay? So then it's simply a matter of solving for the v's, and here I'm going to identify the different v's with their own subscripts. Okay, which I didn't just for clarity before. So then solving each of the three equations, so I'm stacking them up, I would have v hoop. See how much space I have? All right, so bring that up a tad. So I have V hoop, V cylinder, and V shell. Okay, solving each of those, well, for the hoop we simply get GH, just going to be the square root of GH. Okay, and you can see why, right? Because we have the basically shouldn't it be 2GH? No, not 2GH, because we have a 1/2 plus a 1/2. And so that just becomes 1, okay? And then for the cylinder, it will be 4/3 GH, obviously inside the square root. And there we get that because we have over here, we've got a 1/2 times 2/3, which is going to give us a 1/3. And then the 1/3 plus a 1/2 gives us the 3/4. And then the, so yeah. And then 1/2, 1/3, yeah, okay. And then when we solve for v, that's where we end up with the 4/3, because we simply take the reciprocal, okay. And that's why I was looking at the wrong one. I'm like, wait, 1/3 plus 1/2 is not 4/3. Here it is. Here we have a 1/4 plus 1/2. That's where we get the 3/4 from, okay. And then for the shell, we do have a 1/3 plus a 1/2. 1/3 plus 1/2 is 5/6. And then when we take the reciprocal, we should get 6/5 inside the root. Okay, so this one right here is 6/5 GH. Okay? So the only thing that matters then is what planet we're doing it on, our G, our release height, which we found by knowing the overall length of the ramp. And so we just plug in our numbers, and we get that the hoop is moving 3.48 meters per second. The cylinder is moving 4.01 meters per second, and the shell is moving 3.81 meters per second. Okay? And so then the difference between their final velocities would just be comparing them. Okay, so that's our answer really right here. So first of all, there is a difference. And second of all, the fastest is the cylinder. The slowest is the hoop. All right. And how does this compare to a block that's sliding? All right. Well, and compared to sliding block, in that case, we would just have mgh equals 1/2 mv squared, which would give us that v equals the square root of 2gh. which would be 4.92. Okay, because there would be no rotational term. So the 1/2 over here would become a 2 once we solved and isolated for v. Well, that means the block's the fastest. Now that makes sense. Okay, so the last thing I'll say in this lecture before we move on to the second half in the second video. That makes sense because the block doesn't have to spend any of its energy rotating. In other words, all of the gravitational potential energy can get allocated to the translational kinetic energy without having to save or use up any of it for rotation. So that means that the block absolutely would be the fastest translator because that's all it's doing. It's a specialized translator. Whereas the other three objects, the shell, the hoop, the cylinder, they all have to spend energy to rotate. That rotational kinetic energy has to come from somewhere. You can't just create energy out of nothing. So that's why it has to give up some of its translational energy. Okay? Now, furthermore, why is the hoop the slowest? Why is the cylinder the fastest? Because they're respective moments of inertia. The hoop has in fact the biggest possible moment of inertia. And it turns out it's because all of its mass is as far away from the center as possible. More on that in the next lecture. And because of that, it's hard to rotate. It takes a lot to rotate it. A lot of torque. Again, more on that later. So if it's the hardest thing to rotate, then it has to have the biggest allocation of energy going over to its rotational side. Thus, it's going to be the slowest in terms of its translation. Okay? All right, so I hope that all makes sense.